Hi all, and thank you for your attention. My name is Alex Ledbetter, and this presentation is a review for the thesis I performed for my Master's in Cognitive Robotics at TU Delft. The title of my thesis was Evaluating Predictive Coding Video Prediction Algorithm PredNet for Evidence of Structure Learning. It's a quick agenda. There's going to be roughly 10 slides over 10 minutes, and by the end you should be able to understand the research that I performed and be convinced that my results are valid. In preparation for my thesis, I performed a literature review attempting to answer the question, how do humans learn the structure of the world? In short, neuroscience suggested this theory of mind called predictive coding. Now I'd like to walk us through an exercise where we see this structure learning via predictive coding live. If I were to present this image to you on the right and then ask you to predict where will these objects be in the next frame, understanding that this is a still frame from a video, you wouldn't be able to do it. You won't know if the objects are going to rotate or expand or disappear, etc. But when I now show you this video of the environment, we can begin to learn the structure of this environment by predictive coding. We note that there's a white background, some fixed gray occlusions, a bunch of moving colored shapes belonging to two shape classes, namely crosses and ellipses. We'll note that the crosses always seem to go down and that the ellipses always go to the right. We'll note that these shapes are of a random color, size, rotation, and position, but that these do not seem to affect the motion. Now when I present this same still frame of the video environment to you again and ask you where will these shapes be in the next frame, we can apply this structure we've learned on the left here to inform our predictions. So namely, we're going to identify where the shapes are in the scene. We're going to identify if they are a cross or an ellipse. This will allow us to predict that the cross will go down and the ellipse will go to the right. And we see that our predictions are correct. And in summary, we have applied predictive coding to learn the structure of this simple environment, and we've utilized this learned structure to predict the next frame from just a single view. I will point out that what we've just done here is a very intelligent behavior, and so researchers want to know if artificial intelligence algorithms based on this same theory of mind, predictive coding, can perform this same structure learning task. So now we can get into my research. As a brief timeline of the research I performed, so I just completed my literature review and I identified predictive coding as the answer for how humans learn the structure of the world. So my initial plan was to find an existing AI model based on predictive coding and to improve it. But I quickly realized that the published metrics released with this model I had found didn't offer the ability to demonstrate structure learning. The release metrics didn't show if the model was doing structure learning or not. So I realized that I needed to step back from improvement and first evaluate the model on these structure learning abilities first. In order to do so, I ended up needing to create a structure learning data set, and then I evaluated the model on that data set and was able to show that the model did in fact have the ability to perform structure learning. I then investigated how the model was able to do that and then attempted to improve the model against those capabilities. We will now look at the model evaluation phase of my research. First, by introducing the model. It's called PredNet, and it functions as a video prediction model. So in this top row, we will see 3 ground truth videos, and in the bottom row, we will see the predictions formed by the model We're going to note that this data set that was published with the model, like I said, it doesn't allow a clear demonstration of structure learning abilities. We can't point to the objects in the model's predictions and say, yes, indeed, the model understands that this black object over here is a car, and that cars tend to follow the lines of the road, etc. It's too complex of a data set, so I ended up needing to create a simpler data set called the Simple Shape Motion data set. And this data set is going to allow direct demonstration of structure learning capabilities, namely learning about objects and object classes, the states of objects, and class-specific behavioral associations. The data set consisted of these 4 video task environments, and in each task the model is asked to predict the next frame from a single viewing of the state of the environment. So critically, the model must have learned the structure of these environments in order to form accurate predictions. The first task is asking for predictions for a single shape, second task for 2 shapes. In the third task now, object motion is dependent on the state of the object, namely the object will only move if the object is red. And in the fourth task, object motion is going to be dependent on the state of these blocks in the world, and the object will only move if they are green. So now we can see how well the model performed on these tasks. In the image on the left, in the leftmost column, we have the ground truth video frames going downwards. In the middle column, we have predictions from the model, and in the right column, we have the error between the two. In the first frame, we note that the model has predicted blank because it hasn't seen the state of the environment yet. But before making its next prediction, it receives this error signal on the upper right, which indicates the presence of a purple cross. And so now the model must identify where this object, if there's any objects, where the object is, what kind of object, and know that each type of object has its own specific motion. So the model correctly predicts that the cross will go down, and over here in the right image we note that the model correctly predicts that the ellipse, when it's presented with an error signal indicating the presence of a yellow ellipse, we see that the model correctly predicts that that ellipse will move to the right. It's key to remember that the model is trained on a data set of both shapes, so at test time it's just presented with this error signal. It could be a cross, it could be an ellipse, and the model needs to extract from that error signal the correct motion to apply to the shapes. In the second task, it's a little bit more difficult. Now there's 2 shapes to push around. In the left image we note an error signal indicating the presence of a blue cross and a pink ellipse, and note that the model has correctly pushed the blue cross down in its prediction for the next frame and moved the pink ellipse to the right. And same in the right image, we have an error signal indicating a purple ellipse and a green cross, and once again the model is predicting the next frame correctly where the purple ellipse has been moved to the right and the green cross has been moved down. In all cases, shape fidelity could be improved. In the third and fourth tasks, if we could look at the upper box here, we'll look at the class state task. In the topmost row we have the predictions from the model, in the middle row we have the ground truth frames, and in the bottom row we have the error signals. So that first prediction is once again a blank brown, but it receives an error signal indicating that the state of the environment has a black cross in it. It has learned that black objects don't move, and so in the next frame it predicts that same black cross to be in the same position. It then receives an error signal that the object color has changed from black to red, and so it knows that red objects do move, and so in its prediction for the next frame, it predicts that the object will have moved down, and it continues to predict downward motion so long as the object stays red. Eventually it receives an error signal indicating that the object has turned black, and so it predicts the object to be where it saw it in the last frame, unmoved. And it does the same for the ellipses down here, and in the right two images we'll have a very similar story, except now object motion is dependent on the state of the world as opposed to the object. So the object will only move when the world state boxes are green. And in both of these tasks, it's critical to note that it's a little bit harder than the first two tasks, because now object motion is dependent on both the class of the object, is it a cross or an ellipse, as well as the state of the object, is it black or red, or in the fourth task, is the world state green or red. So in summary, we can say that by successfully completing these tasks, we can conclude that PredNet is capable of performing structure learning of objects, classes, and class-specific behaviors, including those conditioned on both class state and world state at a rudimentary level. I'll just quickly introduce the following two phases of my research, where model investigations looked at which aspects of the model architecture enabled these structure learning capabilities. And then in the model improvement phase, I attempted to improve the performance of the model by encouraging it to focus on the distinct objects in the scene and to note those objects' classes directly. That's all we have time for. Thank you so much.